So we'll continue with a couple more from 8.5, and then we'll jump up to 8.7. So the first one I want to do is, I think, problem number 24. If it's not problem number 24, use your imagination and pretend it's problem 24. X minus 1 over x squared times x plus 1 dx. And I think this is even in a nice definite integral, but I want to focus on just the setup for this kind of a problem. You're going to have x minus 1 over x squared times x plus 1. And let's think about how you're going to set up the right-hand side. Do you notice something about the case of problem that we're dealing with? I've given it a name. I don't expect you to know the name, but maybe you do. What am I going to set up on the right-hand side in terms of some partial fractions? What's the general decomposition going to look like? A over x, b over x squared, plus c over x plus 1. So for that repeated linear factor of an x, you've got to have a fractional term for each one of those. Okay. Everything here is going to get multiplied by that LCD. So x squared times x plus 1, x squared times x plus 1, x squared times x plus 1, and x squared times x plus 1. So all those get multiplied by the LCD. We're going to get some great cancellation on the left-hand side. All that disappears. So it's just x minus 1. On the right-hand side, again, some more cancellation. The x's cancel. So you're left with a times x minus, or x plus 1. So that 1x cancels. A times x plus 1. Yeah, that's a really crappy x, ax. How about with the b's? What's going to cancel out there? The x squared term cancels, so b times x plus 1. And finally, c times what? X squared. Now with some clever choices, you can figure out A, B, and C. I'd start out by setting x equal to 0. And that's going to allow you to get rid of this term and solve for b. What else can we do for clever choices? What other nice choices would we have? -1. That'll kill off this term and allow us to solve for c. So real quickly, and I'm not going to go through all the details, you could get b equals -1 and c equals -2 without too much sweat. Once you get those in the manner we just described, then plug those back in so that you can solve for a. So you'll have x minus 2 equals a times x plus 1 minus, plugging in for b, x plus 1 plus, I should have written a minus there, minus 2 times x squared. So minus 2 times x squared. Should I have a minus 1 here someplace? Oh, yeah, thank you. X minus 1. Okay. And now I need to choose another value for x so that I can finish this off. It's up to you. I mean, you don't want to use 0 or -1 because that would kill off our a term. So what's an easy value to choose for x? Yeah, 1 would work. Set x equal to 1. So 1 minus 1 would be 0 equals a times 1 times 2 minus 2 minus 2 again. So 1 squared times negative 2. So that's a negative 4, which I'll put on the other side. 4 equals 2a. So a is 2. Yay! A is 2. B is negative 1. C is negative 2. Overall, that gives me the integral from, of 2 over x. Let's see, b was negative 1, so minus 1 over x squared, minus 2 over x plus 1 dx. This is going to iterate as 2 times the ln of x, minus and minus, let's see, minus exponent. I think that's going to be it's going to be plus 1 over x, or is it minus 1 over x? It's going to be a plus. Yeah. Plus 1 over x minus 2 ln of x plus 1 plus a constant. So just like I said, a little bit more review of that kind of thing. Yes?
When you get to integrating them and you substitute backhand, you can just break them off right away and just integrate them individually.
Yeah. Yes. All right, last comment on this section, and it's problem number 10. I'm just going to do part of this. So problem number 10. The integral of x cubed minus x plus 3 divided by x squared plus x minus 2. Well, this one's a little bit different because of the degree of the numerator and the degree of the denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, you're going to start with a long division. So that's the only part that I want to do of this problem, is work you through the long division. So it's going to be x squared plus x minus 2 into x cubed. Now it's not really here, but what could be understood to be between these two terms? Plus 0x squared minus x plus 3. So if we compare the leading coefficients, x squared to x cubed, I realize I need to multiply this by an x to match that leading term. So x times this gives me x cubed plus x squared minus 2x. The tricky part here is to keep in mind that you're subtracting this. You're subtracting that whole thing. What I find easier than subtracting is to add the opposite. So I'll make that a plus and just change all these signs. So that becomes a minus x squared plus x plus 3. And now this process repeats itself. You have to look at x squared and negative x squared. What do I multiply this by to get this? Negative 1. So negative 1 times this is going to give me negative x squared minus x plus 2. But as before, I'm subtracting that. The way I encourage you to subtract this, and it's completely up to you, but you add the opposite, so that makes this a plus, and this a minus. What's left when I get down to the very last step? Plus 1. Plus 1. There you go. So, how does that help me? Well, it allows me to rewrite my problem. This is equal to x minus 1 plus 1. This is your remainder, so that goes 1 over x squared plus x minus 2. And from here, I mean, this is just a nice distinct linear factors term. So you can do your partial fraction decomposition, and there's no problem integrating that. Did I make a mistake someplace? Oh yeah, yeah, I'm sorry. I guess yeah, that'd be a 2x. So that'd be a 2x here. 2x plus 1. But it still works out the same, that you would have to do the partial fraction decomposition. This is the distinct linear factors case, so it wouldn't work out too bad. But it's a lot nicer now that we did the long division. Whew. For homework, this is section 8.5. Try 1 through 9, 13 through 17, 23 through 31. Those are just the odds. All right, we're gonna just keep going here. But let me give you a little bit of a break. I saw this one earlier. I thought it was pretty cute. Let's see, image. There you go. All right. All right, don't look too close at the background there because it's not very polite. Okay, onward. So we're moving past section 8.6 up to L'Hopital's rule, section 8.7. L'Hopital's rule is pretty slick. It's going to allow us to find limits in very special cases. And do so in a much faster way than we might have done, say, in Calc 1. So in Calc 1, one of the limits that you dealt with was this one. So let's see, section 8.7. We had the limit as x approaches 0 of the sine of x over x. And remarkably, even though in putting in the limits you get 0 over 0, remarkably that limit turned out to be 1. Now, in Calc 1, the proof of this was a long geometric argument. You trap this between two other quantities. Both of those quantities are going to 1, so this one has to go 1. It's called the sandwich theorem. But now we're going to have a more clever way we can solve this. We can solve this. We can prove this in like a heartbeat now. And it's called L'Hopital's rule. Let me see if I can't find it in the book so I don't have to write it down. Yeah, it's on page 558, right here. Let me take care of this for a second. Freeze there. Back here. Good. All right, so here's what L'Hopital's rule says. These two limits, that is the limit of some rational function, f of x over g of x, as x approaches c, and the limit as x approaches c of f prime of x over g prime of x, they're the same. So in other words, you can differentiate these things, and the limit's going to be the same. Now, there's one catch. This limit has to be of a special form. Has to be of an indeterminate form, like 0 over 0, like for our sine function. When we put in 0 for the sine and 0 for x, if you just try plugging in the limit, you get 0 over 0. Well, what is 0 over 0? Don't know. It's not really well defined. But if you get that indeterminate form, then what this is saying is that you can take the derivative of both the numerator and denominator and reevaluate the limit. So let's try it. Limit as x approaches 0. What's the derivative of the numerator? Cosine of x. All right. Without too much thinking, what's the derivative of the denominator? 1. Now, let's plug in the limit, right? What's the cosine of 0? 1. 1 over 1 is 1. So, wow. What could easily take you 10 or 15 minutes in Calc 1 takes you 30 seconds in Calc 2 because you have L'Hopital's rule. It's like, oh, cool. Why didn't you show us that last semester, right? Well, it takes a while. Sorry. All right. There's only so much you can cram into a Calc 1 course. There actually are some books that do introduce this earlier. Ours just isn't one of them. All right. Now, the bottom line, though, is that you need to have an indeterminate form. And there's really a lot of indeterminate forms. Indeterminate form. You could have 0 over 0. That's an indeterminate form. You can have combinations of infinity, so plus or minus infinity over plus or minus infinity. That's another indeterminate form. There's a lot of different possibilities here. Now, when we get rolling on this, 1 to the infinity power, what's that? That's another indeterminate form. Or 0 times infinity. What wins, right? It's times 0, but it's times infinity. So there's a lot of different forms. Basically, though, if you're going to use L'Hopital's rule, you're going to bring it back to something like this. You're going to have to write it as 0 over 0 or some infinity over infinity before you can start applying L'Hopital's rule. Oh, another indeterminate form would be infinity minus infinity. Is this a bigger infinity than this one? Don't know. So let's try a couple examples. We'll start with problem number 12. And let's see, do I have that handout still? I do. Cool. Problem number 12 looks like this. The limit as x approaches negative 2 of x squared minus 3x minus 10 over x plus 2. Okay, there's a couple ways you could work this one. If this was Calc 1, we'd probably do something like this. We'd look at the numerator and say, oh, you know what? That factors. That's x plus 2 times x minus 5 over x plus 2. And what happens? That cancels, right? You can get rid of that. It cancels. And then you plug in the negative 2 into what's left. Negative 2 minus 5 gives you negative 7. Great. No problem. But suppose you tried plugging in the limit here before we even got that far. Maybe here, maybe here. If you tried plugging in the limit, what happens when I plug in negative 2 in the numerator? I get 0. And in the denominator, I also get 0. So I can apply L'Hopital's rule. So extra credit if you can spell L'Hopital correctly along with the punctuation. L'Hopital's rule. Now, interestingly enough, a little historical note. If I remember right, L'Hopital did not actually invent this rule. He paid one of the Bernoulli brothers to be his tutor and to work with him with calculus, and for the right to publish some results. And this was one of them. So I think that's where it got his name. In any case, L'Hopital's rule says that I can take the derivative of the numerator divided by the derivative of the denominator. So let's see if that works here. The derivative of the numerator is going to be 2x minus 3, and the denominator is going to be 1. So this limit and this limit are the same, and if I plug in that negative 2, I end up with 2 times negative 2 minus 3. I get the same negative 7. Cool. Works out pretty nice. Are we okay with our first example from L'Hopital's rule? We're definitely going to get some more here. Let me quickly look at the associated graph of this problem, because I want to point out some stuff about this problem and remind you of some stuff about limits. So I know I haven't given you this graph, this copy, but we're okay here. If you notice, if you looked really carefully, there's actually a hole in our graph. You know what? This one doesn't look like exactly what it should look like. It's close enough. There's going to be a hole in your graph, but what your limit is what happens when you get close to that hole. It's the y value. Now this doesn't seem like quite the right graph, but you are getting close to that y value. Maybe let's look at it on Desmos here real quick. So y equals x squared minus 3x minus 10 divided by x plus 2. So you can see, you can trace and trace and trace, but when you get it right at negative 2, undefined, right? So there's a hole in the graph. But it doesn't matter, because what the limit is what happens when you get close to that negative 2. So as I get close to negative 2, you can see the y value is getting close to negative 7. Right there and right there. Close to negative 7. So what actually happens at the limit doesn't really matter. It's what happens when you get close to that point. So just a little reminder of one of the subtle points of limits. Let's try problem number 14. And let's graph it first, see if we can't come up with a prediction. So it's the limit of the square root of 25 minus x squared. So 25 minus x squared divided by x minus 5. Now what we want to see here is, well, what happens to this function as you get close to 5? So you get close to x equal 5. Does it say from the positive side? Let's see, x minus 5. Yeah. Has to be from the negative side, I would think. Let me just take a quick look here. 14. Yeah, it's from the minus side. So as you get close to 5 from the minus side, where does it look like my y-coordinate's heading? Negative infinity. Yeah. Your graph, your tables, and L'Hopital's rule should all say the same thing. So let's see if L'Hopital's rule says the same thing here that we're seeing from the graph. It should. They should not say different things. So it's the limit as x approaches 5 from the left of the square root of 25 minus x squared over x minus 5. The first thing to always try when you're evaluating a limit is to try plugging in the limit. Plug in the 5. Does that work? No. You get 0 over 0. Shocker. We can use L'Hopital's rule, right? All right, that's what we're trying to practice, so that's a good thing. So let me rewrite this a little bit. Limit as x approaches 5 from the left. as 25 minus x squared raised to the 1/2 power over x minus 5. I think it's helpful to rewrite it before we try and differentiate it. I'll share the duties with you. So you do half, I'll do half. I'll differentiate the denominator. You differentiate the numerator. Fair enough? Wait a minute, I stacked the deck on that one, right? All right, so let's multiply by the exponent out front. That's 1/2. 25 minus x squared. Subtract 1 from the exponent, but I'm not done. What else do I have to do? Derivative of the outside times derivative of the inside. What's the derivative of the inside? Negative 2x. So I end up with the limit as x approaches 5 from the left. The 1/2 and the negative 2 are going to cancel. So this is going to leave me with a negative x. This term right here can be put in the denominator. So it's going to be 25 minus x squared to the positive 1/2 power. Did that help us out at all? Well, yeah. If you try plugging in the limit, you're going to get negative 5 over 0 in some sense, right? Where is that heading? Well, that's headed towards negative infinity, right? You're dividing something which is a constant or, getting close to negative 5 by something that's getting vanishingly small. So this is going towards negative infinity. But we saw that from the graph, right? That graph had essentially a vertical asymptote. It was plummeting towards negative infinity. So this is matching our conclusion that we saw from the graph. Let's try problem number 28. The limit as x approaches infinity of x cubed over e to the x squared. All right. This one's going to be a little bit of a battle, but let's see what happens here. If you try and plug in the limit, what are you getting for the limit? Infinity over infinity, right? As x approaches infinity, x cubed is going to approach infinity. As x approaches infinity, this is going to approach infinity. Question is, do they do this equally fast, or is one faster than the other? One's probably going to be faster than the other. But because it's an indeterminate form, we can use L'Hopital's rule. So it's the limit as x approaches infinity of 3x squared. Now you got to be careful in differentiating that term in the denominator. What's going to happen with that term there? It's e to the x squared times the derivative of x squared, which is 2x. And at least we get a little cancellation here, right? The x's can cancel. So let's do that. So it's now the limit as x approaches infinity of 3x over 2 e to the x squared. All right, cool. Now let's plug in infinity. Or at least think about plugging in infinity. Same thing again, right? So now what do? Yeah, L'Hopital's rule again, right? So let's try it again. In the numerator, what's the derivative of the numerator? 3. In the denominator, I'll get a 2 times 2x times e to the x squared. So why don't you look at that as I graph this one? Let's see if our conclusions match. All right, so what are you getting for the limit? Well, let's look back at our work here. You've got a constant divided by, well, as x approaches infinity, what's this approaching? Infinity. What's 3 divided by infinity going to tend towards? 0. So we should see from our graph that the graph goes towards 0. And that's exactly what happens. This graph gets towards 0 pretty fast. I mean, look, all the way out to 4, all the way, this is essentially 0. I mean, the graphing calculator software here is like, you know what? I don't even want to bother with any decimal places. That's just a 0. So, yeah, e to the x squared is going to grow really big, really, really, really fast. So, yeah, that one's certainly a 0. So that was one interesting case that you had to do repeated applications of L'Hopital's rule. But there's other interesting cases as well. Before I move from problem 28, are we okay with our conclusions here? Let me be very, very blunt here. I encourage you, when you're doing your test, to look at the graph on your graphing calculator. The conclusion on your paper should not differ from what you see on your graphing calculator. If they do, just mark on your paper for me, I already got this one wrong. You'll be doing me a favor, okay? They should not be different. Okay. Let's try problem number 44. Limit as x approaches 0 from the right of x cubed times the cotangent of x. Now this is going to be a different kind of problem, and initially it's not quite in the form of L'Hopital's rule, because as x approaches 0, that first term approaches 0, but as x approaches 0, cotangent is going to approach positive infinity. So I get 0 times infinity. Well, which one wins, right? Is 0 bigger or is infinity tougher? You know, who knows? Now, I want to use L'Hopital's rule, but L'Hopital's rule says that I've got to do as 0 over 0 or infinity over infinity. In other words, I've got to play around with this a little bit to put it in a better form. Sure, we can change cotangent x. How would you like to change cotangent x? Cosine over sine? Good, so let's try that. That's a good place to start. X cubed of cosine of x divided by sine of x. All right. Did that help? Did that make a nice difference? What happens if I try and put in 0 over 0 now? Or 0 now? I get 0 times 1, which is 0, over 0. So, yay. Perfect solution. Donnie. Only if you want it correct. Yes, yeah. yeah, you have to. I mean, the reason for this is that L'Hopital's rule only applies to these cases. So I can't differentiate it here because L'Hopital's rule doesn't apply yet. But when I rewrite it like this, then yes, it does apply, and now I can proceed. The one drawback here that we can't really work around is that you got to use the product rule to differentiate this, right? Oh yeah, a lot of enthusiasm in the class, especially late at night here, like this is. That's going to be 3x squared times cosine of x minus x cubed times sine of x over cosine of x. Okay. Did that help? Well, I think it did. Why don't you see if you can't figure out what that limit is while I try and figure out how to graph this thing? Separately. Yeah, it's a good point, and I appreciate you asking here. You differentiate the numerator and denominator separately. So here I just differentiated that with the product rule, and that's what I got down here. And then sine, I just differentiated that. So yeah, you're differentiating them separately. Do not use the quotient rule to differentiate here for L'Hopital's rule. So yeah, thank you for that. Yes? Let's think here. Let's see. Well, it's derivative of first times the second. So 3x squared times this. Derivative of cosine is negative sine. So, yeah, I'm sticking with the negative there. But I appreciate you checking me. All right. Try and come up with that while I try and come up with the graph. You know what? Maybe I'll do it on the graphing calculator just for giggles instead of using Desmos. Now, one thing that has to be true in terms of graphing this is not true of my current setup. Can anyone see a fatal flaw before I hit the graph key? Yeah, it needs to be in radians. Calculus is done in radians, period. If you tried to graph this right now, it'd be misleading. So let's go over here and set up radians. The other thing I did is I set up my x-axis, but I didn't bother setting up my y-axis. Make your calculator do that. Hit the zoom key and then 0. That's zoom fit. And it'll adjust your y-axis to fit your graph. And hopefully we get a good graph. Wow. Little spike there. Okay, see some spikes. Yeah, it's a heartbeat and a P wave and all those things. So we are getting some spikes. What's going on with that graph, though? That bothers me. Should be a little bit more straightforward. How am I getting the spikes? Oh, I'm getting the spikes when well, I shouldn't do that. Let's see, I got x cubed over tangent of x. Yeah, they are, but oh, wait a minute. All right, I'm being kind of stupid here. The limit is not as x approaches infinity. It's the limit as x approaches 0. So let's go back to the graph here. Let me readjust my window from, like, say, 0 to 1. Zoom fit. All right. Let's take a look where the graph is going. As you get closer to x equals 0 along the x-axis, where's the y value going? Closer to 0, right? Assuming that's the point 0, 0. Yeah, it's getting closer and closer to 0. And that should be your conclusion here. If you try putting in a 0, you get 0 times 1, which is 0. 0 times 0 is 0. So you get 0 in the numerator and 1 in the denominator. So 0 over 1 is 0. And at least our graph matches that. Cool.
So our final answer would be 0?
Yeah, final answer is 0. Yeah.
You do not have to write that graph or
No, but the graph should match your conclusions here. Let's see. Negative 1. Y min. Yeah. Rats. All right. I'm not going to play with it, but the graph should be saying the same thing as what L'Hopital's rule is saying. All right. Problem number 50. limit as x approaches infinity of 1 plus 1 over x to the x power. Now, if you try to plug in, the limit, 1 divided by infinity would be 0. 0 plus 1 would be 1. You'd have 1 to the infinity power. Well, that's certainly indeterminate, but it's not of L'Hopital's form. Now, there's a trick here that we're going to play to kind of get around this. And might do well to try and catch this trick. Let me let y equal this term here. 1 plus 1 over x to the x power. I want the limit as x approaches infinity of y, or of this term. So I want this limit as x approaches infinity. So it's going to be the same as the limit over here. Limit as x approaches infinity of y equals the limit x approaches infinity of 1 plus 1 over x. Now, the unfortunate part is that this is not of L'Hopital's rule yet. It's not in the form of L'Hopital's rule. And what I can do is I can take the log on both sides. So I'll take the log of y, ln of y, sorry, I got a little bit overzealous here. Let's not put this limit here. Let's just keep it on the right-hand side. Thank you. If I take the log of this, it'd be the log of this limit, and what I can do is I can interchange the two operations. Instead of take the log of the limit, I'll take the limit of the log. Limit as x approaches infinity of the ln of 1 plus 1 over x to the x power. Now, does that help me out a little bit? Well, actually it does. This term can come out in front. So I'll rewrite that as the ln of y equals the limit as x approaches infinity of x times the ln of 1 plus 1 over x. And it seems like I haven't really gotten anywhere, because instead of having 1 to the infinity power, now I've got infinity times 0. I still need to rewrite it one more time, and this one's going to do it for us. Limit as x approaches infinity of the ln of 1 plus 1 over x. Instead of multiplying by x, what if I divided by 1 over x? Let's think about that. Dividing by a fraction, you multiply by the reciprocal. So instead of dividing by 1 over x, it would be the same thing as multiplying by x over 1. So these two are the same. They're equivalent. But what did I finally get to at this last step? Yeah, indeterminate form. That's my numerator. That's my denominator. If I try plugging in infinity, I have the log of 1, which is 0. 1 over infinity is 0. It's finally 0 over 0. So, a lot of work to get here, and a little bit of work to get us out. But now that it's 0 over 0, we can finally apply L'Hopital's rule. I better do it soon, because Kevin's getting anxious to get out of here. All right, me too. Let's apply L'Hopital's rule here. That's going to be the limit as x approaches infinity. Let's do the denominator first. Remember, the denominator you can think of as x to the negative first power. When I differentiate that, that's going to be negative x to the negative second, or better yet, negative 1 over x squared. So that's going to be the derivative of the denominator, negative 1 over x squared. Now the numerator, we're differentiating a log term. So I'll get 1 over this, 1 over the argument, times the derivative of the inside. Here's kind of a nice, happy little coincidence coming up for us. When I differentiate the inside, it's the derivative of 1, which is 0, times the derivative of 1 over x. Well, we just calculated that, right? It's right here. So it's negative 1 over x squared. You see our happy little coincidence? Those two terms cancel each other out. So what we're left with is the limit as 1 approaches, or x approaches infinity, of 1 over 1 plus x. Yeah, that limit is just 1. There's only one little drawback here. That's the natural log of y. I don't want the natural log of y. I want y. So what does y equal? E to the first power. If you were to look at this graph on your graphing calculator or your favorite graphing software, y equals 1. Y equals 1 plus 1 over x raised to the x power. I didn't put that x in the right spot. Raised to the x. There we go. You should see that it gets closer and closer to this graph, y equals e. So there you go. As you go out towards positive infinity, it's getting closer. Oops. I still must have typed it in wrong. E. No, that's right. Okay, yeah. Yeah, it's getting closer to E. Okay, that's enough for one day. Good job. Let me give you some homework. Try 1 through 59. Actually, you know what? You can skip some of the early ones if you want, like the ones that involve the tables 1 and 3. You can skip those. So 5 through 59, and let me give you a couple more that you can skip. You can skip 41. You can skip 29, although I should really cover what we do with 29 at some point, because there's a little subtlety there that's kind of neat. And you can also skip 39. Okay. Test next week. We'll cover up to and including section 8.7. We did not cover 8.6, so you're all set there. Have a good one.
Wait, what was the first section?
See ya. First section, where did the last test leave off? 7 point. Let me see if I got.
Yeah, the last section of 7 is check
Like, it was 7 something. That's what I'm tired about, but...
Let's see.
Oh, by the way, do you guys want the SI section to start at 3:30 or 4?
So it should, yeah, 7.7. 7.7 through 8.7.